Thank you so much for your kind introduction, Chairman. And my name is minwon from National University. And it is a great honor to have such a good chance and to introduce my research work and my colleagues' work together. The title is Korea Project for Developing Basic Technologies of 10 megawatt floating wind power generator with HTS magnet and test field facility, and sponsored by the CAPCO. Okay, this is a very the designed graph, maybe comparing with the conventional generator and motor, and with the superconducting and rotating machine. And you can see, and this x-axis is torque, and the y-axis is power. And most of the case, and the conventional and the copper and rotating machine is located here, this area, and with the very low and torque. But applying to and superconducting magnets, then you can get much higher torque, like this. This yellow color, it is related with the superconductivity HTS magnets. And long time ago, and American superconductor, and they developed 36.5 megawatt and rotating machine here. And also a few months ago, and the European Union, they announced that an ACASC project is and the good results with the real 3.6 megawatts and the wind turbine. However, and both of them are almost the same and torque. But, and a lot of the new idea was announced and then also released with several papers and with the 8 megawatt and 10 megawatt and 12 megawatt wind turbine. However, such a big megawatt wind turbine, it is a little bit very high in the torque area. So because of this reason, still, and we never go in this area, but we try to make a new program in order to overcome such a high torque and rotating machine. So when we proposed almost 3 years ago, and it was started in 2018 March, and then it will be finished exactly 1 year later, and totally $6 million from fully sponsored by the utility company, and for 3 years. The target is 10 megawatt class HS generator, and the design, and then 3 and real magnet, and also floating offshore wind turbine, and the technology will be developed with this machine. And also, our university, 창원 National University, is mainly deal with this HS generator part. And then University of Ulsan is a floating system. And the University of Jeju National University, they are grid connection and technology and economic analysis, and also some part of the magnets. And also International University is integrated the control system of the offshore wind farm. And then Professor Andong National University, he is now doing this work, for example, HS coil for large scale HS wind generator. This is the consortium with the 5 universities in order to achieve this very top target. So this is a basic concept of the 10 megawatt wind generator. And so target is, and the rated power is 10.5 megawatt, and the rotating speed is approximately less than 10 RPM. So because of this reason, as just a few days ago, I introduced with some school, and most of the big size of the wind turbine, there is no gearbox. The meaning of the no gearbox, it is the rotating speed of the blade is directly same with the rotating speed of the generator. Then maybe because of the low rotating speed, it means that very high rated torque. So rated torque is approximately close to the more than 10 meganewton meter. You cannot imagine and 10 meganewton meter. And in order to get the energy from the blade, and then with very high torque, there is a mechanical never connected between rotor and the stator. So energy and moved from the rotor to stator or electrically and moved to with the magnets. Then the high torque is an unavoidable problem. So this is a basic, very basic design of the one coil. You can see, and this is and the critical current is like the 77 kelvin. However, real operation current is more than 300 amperes. And also the maximum magnetic parallel field is close to the 3 Tesla. And so this is you can see this is a weak point. We can understand this is a very weak point. And also, critical current of the HH generator considering angular dependency is very important in order to design. And also 35 Kelvin. At that time, the IC is here, so we measured and then also we designed in detail about the magnets. Also, you can see how many poles, 40 poles. And the 1 poles of the magnet, just previously I introduced that. So how many wire you required? Is more than 100 kilometer with 12 millimeter width. Is huge amounts of the wire required. And the total weight is 120 and 4 and the tons of the required. So, and also insulation type is a metal insulation. And so there are a lot of different types of the insulation technology. So we apply the metal insulation because, and a few years ago, and induction heater, and more than 300 kilowatt class induction heater is fully commercialized, and then now they are making the 1 megawatt class induction heater using and Repco and also magnesium diboride. And the cheap price of the machine is and the long length of the heating time it is magnesium diboride, and short time the heating up time it is and they are using the Repco. At that time they used metal insulation technology. So it is comes from the laboratory, and so we use the same technology of the metal insulation. Okay, it's not working. Okay, and also, this is a schematic and the diagram of the wind turbine, and with the 40 force, and we will apply the 10 cryostat. So in order to make full cryostat system, it is very difficult to do, and as you know, and so we divided every 4 pores with the 1 cryostat. And also, as you know, and the magnet has to be operated under very close to the 30 Kelvin. However, the cryostat, it is a circumstances approximately 300 Kelvin. So very big difference gap of the temperature. And also because of the very strong and force, because of the torque. So the supporter is very important. How to design the supporter, it is very important things. So this is the part of the materials, so what we used, and density is what we used, and you can see with this graph. So this is a very cartoon scale and the supporter design. It is not the real one, however, it is very similar with the real one. And so, this has to be maybe overcome to such a high torque. Finally, using some analysis with the FEM analysis, and then also the MATLAB and the hand calculation. And we got the results with totally 10.5 megawatt is we can obtain with that design. And the rated torque is 10.5 meganewton meter is right. And also we calculated and every part of the system. And for example, cooling system is 3.5 tons, and the cover is 13 tons, and we measured because our tire of the wind turbine with the superconductive, it is the reduced weight and then making the small size of the machine. That is the target. So every time we measure exactly and what is and the weight of the every part of the wind turbine. Okay, we did also some economic and analysis. And for example, and the capex, it is very important, the capital expenses. And economy evaluation, we compared with PMSG is a permanent magnet synchronous generator. Before introducing PMSG, maybe you have seen the lots of the wind turbine when you travel all over the world, and the cylinder type, same of the nacelle, it is not synchronous generator. The most of cases, it is an induction generator with the gearbox. But disc type and the generator, it is, in the most of cases, it is a PMSG, permanent magnet synchronous generator. It is a direct-driven wind turbine. Sometimes, and they are using electrically excited, and the coil was used for the synchronous generator. However, in the most of cases, it is a direct-driven and the disc type. And also, superconducting and the synchronous generator, it is very same and figure with the PMSG and the EESG. So we compared with the PMSG type wind turbine like this. As you can see, and also the balance of the cost and the capex, and then also the turbine capital cost, of course, superconducting is expensive, and also capex, it is also superconducting machine is very expensive compared with the PMSG. But however, just only the total capex is just $5 million US higher than in the PMSG. And in case of the OPEX is operation expenses. You can see we have a cryogenic system. It is very difficult to say that superconducting power application machine is much higher in efficiency. As my understanding, it is not exactly true. But because of we have a cryogenic system and operation, and also operation cost with some very well educated and high engineer has to be employed. So it is also cost. So the efficiency is almost the same. However, the power capacity, in case of the cable and the small size, and we can reduce the total size of the power delivery with the same power. And also in case of the wind turbine, we can reduce the size and weight. That is the main point. So finally we could get, even though OPEX it is much more expensive than the PMSG. But however, and this is a wire price now, and $0.2 per ampere meter right now, and we bought, and a lot of wire already we bought. But maybe if you change it to like this way, then in the future, I'm sure that much close to the same and with the PMSG, but slightly expensive. But it is no matter. Maybe if you would like to buy 2 units of the 3 megawatt wind turbine, then you would better, even though 6 megawatt 1 unit wind turbine, much more expensive, you would better buy 1 unit of the 6 megawatt wind turbine. It is a much better choice. So, higher output power, it is a very good advantage, even though a little bit expensive there. So, and it is I'm sure that in the future, and the economical benefit is also appeared soon. Okay, then, and the next time, and the next step, and we consider that our support can withstand with such a high torque or not. That is the point. And lots of the engineers and gather into at the same places and to discuss, in order to discuss this problem. And then you can see, in case of the load, how to generate the strong torque. And the generator output, for example, 3 output terminal ABC or UVW, there is no current is flowing through the output terminal, then there is no torque between state and rotor, as you know. But slightly small torque is exists because the rotor makes some eddy current inside of the stator and the teeth. There is very small size of torque. But load is connected because of the EMF is generated by the and E equals to BLV. Then the output voltage is connected with the load. Then the strong, very high current is flowing. Because the high current is flowing and through the stator, then through stator makes very high magnetic field too. So between rotor and generator, strong torque is generated. So as you can see, this is a no load condition. This and the circle is load condition. You can see tangential. Oh my God, this name is some. So sorry about that mistyping. Tangential force is generated 71 kilonewton. It's very strong torque, and even the one and the magnets. There is a problem. It is maybe 2 months ago in Kyoto. You have seen already this and the slides before. And you can see with the low load condition, just only small eddy current of the teeth because of that displacement of and the magnets is slightly moved. However, in most of the case, state and the rotor and the back iron and rotor and the state, it is almost compensated each other, so that there is no such a strong torque. And also tangential force, almost 2 kilonewton and 2 kilonewton. It is very small. However, in case of the load condition, this is a strong displacement. This is why I emphasize almost 500 times. Anyhow, not 500, I don't exactly remember that, sorry about that. So it is moved like this way. So it is because of the strong and tangential and the force is generated by the torque. So superconducting field coil and can generate a high magnetic field, but must withstand such a strong force. Okay, then, and here you can see an echo swing and then superconducting, American superconductor, they already maybe succeeded and the 79 kilonewton and the force. And our target is 71 kilonewton. Much smaller than that of from the American superconductor. But you can see here, a short diameter machine like a motor, and it is for cryostat is here, and it is connected to the dielectric, and then this is shaft. So this shaft and then magnet is the same temperature. So most of the reaction torque is generated. Torque disc is okay. It's very strong, and the temperature is the same with the other magnets. So it is a problem, but however, is not so difficult with this one. This one you can see, and the long diameter and the machine here, and this machine here the temperature is 35 Kelvin. Here the temperature is 300 Kelvin. So the torque is generated here. So we have to overcome such a high torque with the magnet itself. That is a problem. Okay, so in order to achieve such a high technology, and we made a very simple and the machine. The name is the performance evaluation system. So modeling of the PES is a performance evaluation system based on the 10 megawatt wind turbine. And then so we will make 3 magnets like this, and then also we ordered already the stator like this. Such a very similar with and the linear motor. And so 40 and the units of the knees in case of the wind turbine, but in case of the PES, performance evaluation system is just only 3 units of the pores. and also, and then the output voltage is just only 190 volts is enough to overcome that. So 3 magnets poles are required to make a pole pair and the 2 poles. It means that, and the 3, even though we established the 3 magnets, but the output performance is very similar with the 2 poles output performance. Okay, in case of the stator, and we attach the UVW or ABC, and with the different and current sources like this, it is connected. Because we can, if we have a lot of money, and we can make AC source connection and the stator, but it is not such a big money. It is meaningless in this system, because our system is just only to measure and our magnets withstand with a strong torque, or not only. So we need just only DC current. And so you can see, and the conceptual design of the generator is a 71.5 kilonewton, but PS is a 72.2 kilonewton. There is no error, almost close to the with the real 6. Here, it is very important graph, because the maximum torque is generated with 1 point and within 1 cycle. And here you can see A, B, C, and in case of the different and ABC and the 3-phase machine, and we send the different and the size of the current. In case of the B is 1,500, and A and P is the opposite direction of the 500 and 700 we send, then we can get the 72 kilonewton and the very high and torque, also force. Okay, here you can see the low load condition and the load condition like this. This is a generator analysis. However, in case of the performance evaluation system, if we apply the AC sources, we will move like this. But DC source, no move, just only and like this, and the shape will be generated. So same force, stress, and displacement. And some people can ask, how about fatigue? Still, our design and our machine and the fatigue analysis is not and ready to do. And so future, and if we apply the AC sources, and if we apply an AC stator and the machine with a very strong and the stator with the AC, then we can do that. However, right now at this stage, we just use DC sources. Okay, this is a cross section of the machine, and like this, and you can see, and this. And the frame is very important, and frame has overcome such a high torque and the force between stator and rotor. Is a very important thing. Also, frame has to be non-ferro and material in order to reduce the magnetic field flow, and just only magnetic field is flowing just on the stator and rotor itself only. Okay, so this is a stator, and this is the same force with the generator, and it will be generated. And as you know, the gap of the, there is the most of the conventional rotating machine, there is only one gap between stator and rotor. Electrical gap and mechanical gap is the same. However, superconducting machine, electrical gap and mechanical gap is different. And the superconducting machine, because of the cryostat and the stator, it is the gap, it is a mechanical gap. But electrical gap is rotor magnets, and also the state coil. That is electrical gap. So unavoidably, and the superconducting machine, and a little bit and longer and electrical gap, and comparing with and the other and the conventional machine. So there is some disadvantage there. So, and our machine, we can adjust and the mechanical gap with some maybe moving of the cryostat. Then we can measure more in detail about that, and much smaller force we can adapt, and much higher force we can do that too. In case of the cooling system, and it is and the neon and the condensation part here, and cryoblast, and also helium circulation pipeline is attached to the HTS magnets. And also, and this is a 24/5 Kelvin operation. And also, this is a neon helium mix exchanger, and the work with like this. And also, this is an inlet temperature and hourly temperature, and approximately less than 30 Kelvin with helium gas. This is our target. It is all well and designed, and this year, and from maybe March, and we will start to buy. And also, this is a schematic diagram of the whole systems, and also heat loss is approximately 100 to 120 watts, and also weight is just only 2 times with this machine. It is a very fully same and structure and same in the design of the full 10 megawatt wind turbine. As I said, in case of the real wind turbine, our design is we apply the 10 cryostats and with the 4 pores and 1 cryostat. It is, but in case of the PES system, we apply the 3 magnets like this. Okay, next, this is a frame. As I said, frame and overcome such a high torque, so it has to be also analyzed with some and FM analysis. It is made already done, and also this is the frame withstands very. So it is now it is okay. And also stator, and now they are making. So within a few days later, and they will deliver to our center. So, and this is a state part of that. So finally, now, and in case of the magnets, it is now already designed finished. So 1 megawatt is now in the making now, and 2 more magnets will make. We will make within a few months later. So this is the final and the schematic diagram of that. And then finally, the size will be 6 meter and 6 meter and the XY length. And height is more than 3 meter. And so maybe next year, MT or somewhere in the big conference, then I can introduce the results of this machine and what happened and the results. The support is broken or not, we can fully introduce about that. Okay, I will go to another area. This is the first time to introduce, and also nowadays, as you know, and virtual reality and augmented reality is a very important part of the industry. However, in case of the superconducting society, never used such a technology before. So I would like to emphasize also to persuade our money maker and in order to persuade the foundation, I make this kind of the idea in order to introduce more in detail about the superconducting machine. So it is not so difficult. It is very easy. And for example, and design with the calculation with Excel, and you would better make just only in the script, and you design easily, and then, okay, I have 1 more minute, 10 minutes more. Okay, 10 minutes more. And then 3 models designed with CATIA or SolidWorks, no problem. And also an FEM, COMSOL, and magnets, whatever you can use it. And then with some other machine tools, then you can easily introduce and design with this and simulation and virtual reality is totally same. And so, and it is not difficult to do that. So our laboratory, we already started this idea, and in order to persuade the money more and to the government side and also the utility people persons. This is technology, just a script, and I will pass. So already we designed with CATIA and also the SolidWorks. Already we did it. However, always we introduce this and the figure only one slide, only just one PPT slide only. But you can see, and it is also well designed. Just only this machine, and we can easily go to like this. Okay. It works well. Sorry. Oh. It's not working. Okay, another sensor. Sorry about that. It is done by my laboratory, just with and the virtual reality Google, and we wear that only that. This is one of my students, and they did, and then they wear the Google, and they can see the inside of the machine easily. And so this is just a very short example. And for example, this is another example. This is magnets. This is superconducting magnets with 3D analysis. Okay, the design inside how they well made or not, and easily we can see that. And also we can see more, maybe then very interesting. This is displacement, and how displacement, how supporter, and we understand with that. And also this is magnetic fields. And the magnetic field inside, what happened, and also we can see the inside and the outside, and what happened. And easily we can see that. So, and in order to, displacement too, and then also temperature, no problem. We can do that with this technology. So nowadays, and a new machine, for example, in order to get maybe more in detail design, do that, maybe we have to go to the next step of the virtual reality. And so you can see this moving of the supporter, what happened inside. You can easily see that. So I'm sure that now, long times ago, we stopped at the just only and the metal lab and the hand calculation, and the next step is finite element method, using some console and some and other magnets and other tools. So we have to go to the next step. In case of the wind turbine, is a very good example, and in order to apply the such idea. Okay, so this is a scenario of the research, and so in the virtual reality wind turbine, and maybe using the superconducting technology, why it is much smaller than, why it is much lighter than, why it is much higher torque than, and we can using this technology next time, and then maybe some poster section with some conference, and we will bring the machine, and we will show you and what happened inside in detail about the wind turbine with the superconductivity and technology. Thank you so much for your attention.